Okay, yeah, please, Nicolina, whenever you're ready.
Okay, so hello everyone. So I will give rather an overview of some work on a special class of manifolds, which are called kata manifolds, and especially on some Tori constructions on this. And this is based on joint work with Alexandra Oteman, Massimiliano Pontecorvo, and Matteo Ruggero. So the plan will be first to introduce the class of kata manifolds, and then to discuss existence of different special Hermitian metrics on this, and then to present to you the Tori constructions. So the story of kata manifolds starts from the story of classification of compact complex surfaces of class 7. And so in general, the story of compact complex surfaces in general. So one of these classes of compact complex surfaces is named class 7 when we say that the first Bethe number is 1. So these are surfaces which are not algebraic, not scalar. And this is essentially the only one which is left unclassified. And for the ones which have 0 second Bethe number, we have examples which are given by the Hopf surfaces, so quotients of C2 minus 0 by Z, or some group containing Z with finite index, elliptic surfaces over CP1, or some Inoue-Bombieri surfaces, so which are constructed in some way as quotients of H times C. And we know that these are all of them when B2 is 0. But then for the first examples with positive second Bethe number, this appeared quite late. So they were constructed by Inoue in the 70s. And the first ones that he constructed were obtained as compactifications of, again, some quotient of C times H by a group coming from a chosen number field with 2 cycles of rational curves. So he gave a rather complicated construction, but then later Oda reinterpreted this construction in terms of toric geometry. And so he reconstructed them, but with toric geometry. He also constructed some other classes which contained elliptic curves. And these were essentially all the surfaces that we knew at the time of class 7, if Bethe2 positive. And then
can you say what do you mean by minimal in the first slide?
Yeah, minimal means that they are not blown ups of some other surfaces.
Okay.
So they contain no -1 curve, we say. So exceptional
Thank you.
curve coming from that. Okay, so then around that same time, Kato, in 77 precisely, gave a general construction of a class of manifolds, complex, in any dimension, but which in dimension 2 gave many examples of class 7 surfaces, and in particular covered all the surfaces constructed by Inoue. So this is the general construction. So first of all, I should say what a spherical shell is. So you have a complex n-dimensional manifold. You think about the standard sphere in Cn and of a standard neighborhood of the sphere in Cn, so given by this S epsilon. And then you say that the spherical shell in the complex manifold is an open set which is bialomorphic to this neighborhood of the sphere. Yes, in other words, it's a sphere but embedded together with a small holomorphic neighborhood inside. So any complex manifold contains such a thing. So if you just take a ball as a chart in it and then a neighborhood of the boundary. But then this is not so interesting. And we say that this spherical shell is global when it does not disconnect the manifold. And then this becomes more interesting. Yeah, so in particular, you can think of a torus, for instance, and then any small neighborhood of the circle will be a spherical shell. Or more generally, any higher dimension, so any Riemann surface with genus positive. But usually we are not interested in dimension 1, rather in dimension 2 or more, because that's also when different things start to hold. And such manifolds, so containing such a global spherical shell, are called kata manifolds. So, as I said, Riemann surfaces have those, but we are usually not interested. And another let's say, the first easy example, but which is still not so easy, are given by the Hopf manifolds. And you should think of Hopf manifolds as generalizing elliptic curves. So these are quotients of Cn minus 0 by a group generated by a contraction of Cn, so fixing 0. And if you just look at the sphere in Cn, or a small neighborhood of the sphere in Cn, and the Fitts image in this Hopf manifold, this will not deconnect the manifold. And in fact, when you take out the sphere from the manifold, you can identify this as precisely the ball minus f of the ball, which is in fact a fundamental domain for the P1 of a Hopf manifold here. And so this does not disconnect, and this is really the first example of Hopf. And now the fact is, if you even just look at this already, you have a big class of this manifold. So f could be just given as multiplication by complex numbers, but it can also be much more complicated. And so this is already a very big class of manifolds. But still, it's small compared to all the Kato manifolds. So in fact, Kato also showed us how they all appear. And he gave us this general construction, but they all appear by this general construction, which is sort of similar to what we saw here. So the point is, you start from the ball in Cn, the standard ball. Then you take a proper modification of this ball over a finite number of points. So a proper modification means a holomorphic map to the ball from some other manifold, which is biolomorphic outside this finite number of points. And also proper means that, well, the preimage of these points will be something compact, and it has to be of codimension 1 in this new manifold. So examples of this are, of course, blowups, but they can also be more complicated than just blowups. They can be locally blowups, but globally not blowups. So you start from something like this, and then you also pick so to say, a chart in this modified blow up. Well, in this modified ball. Sorry. So this means you are picking an embedding of your small ball to this modified ones, but so that the boundary is also inside, in the interior of the modified ball. What you do next is you take out this smaller ball, sigma of b. You have a map which goes from the boundary of the modified ball to the boundary of sigma of b, which is even a locally biolomorphism near both boundaries. And you use this map to glue these boundaries together so that you get a compact, complex manifold, which in particular contains a spherical shell, where the spherical shell will be precisely given by a neighborhood of this boundary, which is now identified together. Yeah, so you see that in the Hopf manifold from before, this is precisely what happened, except you had no exceptional divisor. The pi, the modification was just the identity, and all you did was to just pick one chart in the ball, which was given by this contraction F. And so from any such data, so modification and an embedding, you construct a manifold which is a Kato manifold, and we usually call this a Kato lattice. So the remark that I made before is already if you just take a PID identity, you get the Hopf manifolds, and then the germ can be identified as just the embedding. More generally, if when you embed the small ball, you do not touch the exceptional divisor, so that you land outside of it, then you can see directly that this gluing map commutes with the modification. So then you could also just glue first and then modify. So what you actually get is a modification of a Hopf manifold. So the really new examples which appear and which are really different from the Hopf manifolds are when sigma of the modified points will touch the exceptional divisor. But however, even when this happens, you can still always analytically deform sigma in the direction which is transverse to the exceptional divisor, so as to get outside of it. And while doing this, you can construct an analytic family of deformations of your Kato manifold to a manifold which is modification of a Hopf manifold. So this was done by Kato, but I mean, I hope it's clear that it should work. And the general fact is that all of this construction kind of depends on germs. So we work with one ball and its modified ball, but you can always change the fundamental domain of this story and always take a smaller ball and then its pre-image by pi here and rework with that. So that essentially by some different, so by this kind of arguments, you can always reduce to the case when only one point is modified and the other ones you can forget about them. Because then all that will matter is where sigma of this point will go, on which divisor it goes, and the other ones you can arrange yourself so that sigma of B will not touch the other divisors. So you can forget them because you can always just modify later your resulting manifold. So we'll always focus and assume, in fact, that you have one modified point. This point is 0. You can always change coordinates so it becomes 0. I mean, this is it. So what we draw here is really, again, as for Hopf manifolds, just a fundamental domain of the fundamental group on the universal cover of your Kato manifold. So in other words, the universal cover of the manifold is obtained by gluing Z copies of this modified ball minus sigma of B along again the boundaries, but now you will of course glue each boundary to the boundary of the next thing using the same map. And P1 will simply act by sending one copy to the next one. And because now in this copy of the fundamental domains, you always have two different sort of boundaries, one pseudo-convex, one pseudo-concave, you have a natural orientation. And choosing this natural orientation, which depends just on the complex geometry of your complex structure on your manifold, gives you a unique, so a natural generator of the fundamental group. In other words, gives you a canonical isomorphism of P1 with Z. And so not only is P1 Z, but even in a canonical way, if you take this convention depending on the complex geometry of the manifold. So going back to these class 7 surfaces, there is the famous global spherical shell conjecture, which was first stated by Nakamura in 1989, which says that any minimal class 7 surface with positive Betti number should be one of these things, so a Kato surface. So this conjecture is still open. Of course, we don't know any other example of class 7 surfaces. But there are some results in this direction. So first, Nakamura showed this only up to the formation equivalence. So in other words, not really, but well, he actually showed the following thing. He showed that if you have a class 7 surface which has a cycle of rational curves, then this is a deformation in the large of a blown up surface, Hopf surface. In other words, he constructed a family in which the central fiber was this surface with rational curves, and the nearby fibers were all blown up surface, Hopf surface. So this is similar to Kato surfaces, but of course he could not deduce that S is a Kato surface. Then later, Dlusky, Klaus, and Thomas showed that if a class 7 surface has B2 rational curves, then X is Kato. And so then the question was to show that the class 7 surface has indeed B2 rational curves. And this is so far achieved for B2 equal to 1. So Telemann showed in 2005, then when B2 equal to 1, then any class 7 surface has a rational curve. So then using this result, we know this conjecture for B2 equal to 1. In fact, Telemann also showed for B2 equal to 2 that there is a rational curve, but he did not show that there are 2. So because of this, it's still, even in B2 equal to 2, this is still open. So this is the story concerning the initial motivation concerning Kato manifolds. But now we looked at these manifolds motivated by rather Hermitian geometry. So trying to look for special metrics, or rather special new examples of manifolds admitting special metrics. So
Sorry, when you
Yeah.
say that there are V2X rational curves, you mean disjoint or just different? What is exactly the statement about that?
I mean different, not disjoint.
Okay.
Not disjoint, because they will not usually not be disjoint. They will form either one cycle. So if there is one, it will always close itself. It will always has a node, in fact. If it will be more, then they will usually form either one cycle or two cycles, and not more. This is known, in fact, by work of Nakamura. So there are many different sort of classification results, knowing that you have many rational curves which stay in different configurations. Then we know it's a Kato manifold. In general, we don't know. But so here you just ask B2 rational curves.
Okay.
But they will not be disjoint. And yeah, I mean, this is the one main remark is that, again, since these are non-algebraic surfaces, it's very hard to know if they even have any curves in general. And this is one of the big problems, is you have no meromorphic functions on them. You have no objects which will give you sections of things which will give you, like, the zero locus will be of this curve. So there are very few holomorphic objects which will then give you geometric, like as vanishing places or so, geometric separated curves.
Okay.
So this is just finding the two rational curves is the question. Yeah. Okay. So going to Hermitian geometry, then the remark is, of course, has the fundamental group is that the first Bethe number is 1, so odd, so they are not Kähler. And then there are many generalizations of classes of Hermitian metrics, which of course try to generalize the Kähler condition. I just name a few of them, which are, well, the ones at which we looked at on Kato manifolds. So there is the balanced condition. So here, of course, when I say Hermitian metric, I actually identify it with the 1-1 form which it defines. So this omega is actually 1-1 form on the manifold. And then you say that a Hermitian metric is balanced if n-1 power is closed. Say it's strongly Kähler with torsion or pluriclosed with the d bar of omega is closed. Say it's Hermitian symplectic if it is the 1-1 part of a real D closed form. And you also have the notion of strongly Goduchon metrics, in which you ask that del of omega n-1 is d bar exact. So this is strongly Goduchon because usually Goduchon is just that del of omega n-1 is d bar closed. So all of these notions appeared in different settings depending on what sort of properties you wanted to generalize from Kähler geometry. But also the remark is that there are different inclusion relations between these notions. So you can see very easily that balanced implies strongly Goduchon. Also that Hermitian symplectic implies strongly Kähler with torsion, simply because this small omega is real and declosed, or just declosed. It gives you that del omega is d bar exact, so in particular d bar closed. And then it was also remarked by Yao Zhang that on a Hermitian symplectic manifold, you also have a strongly Goduchon metric, which will not necessarily be the same, but you obtained it from taking this real form. You take its n-1 power, it's n-1, n-1 type of this, and then they show that this is positive, so it has to be the n-1 power of some Hermitian metric, and then it also has to be, so del of this has to be d bar exact, therefore the metric is strongly Goduchon. So the strongly Goduchon notion was essentially introduced because it gives a notion of Hermitian metrics which is open under deformation, and also because it generalizes directly or not both the Hermitian symplectic and the balanced condition. And exactly using this, we showed that, well, Kato manifolds admit none of this. Well, maybe possibly under certain hypotheses. So first of all, we show that Kato manifolds just admit no strongly Gaussian metrics, so also then no balanced and no Hermitian symplectic. And also, if the complex dimension is at least 3 and the odd number H12 is 0, then also there are no strongly Kähler torsion metrics. Of course, here the remark is that if the dimension is 2, then strongly Kähler torsion is the same as Gaussian, and then of course there are such metrics. Another remark is that this cohomological assumption, I mean, we can show that it holds on some class of Kato manifolds, and we believe that it should always hold. So this hypothesis here should not be necessary, or rather just always forfeit. But we couldn't show that, so we have this. And this really just follows by applying different results known about these structures, just known already from the literature. So first of all, as I said, the strongly Gaussian condition is open under the formation. And also the strongly Kähler torsion is open under formation if you also assume this H12 equal to 0. Yeah, so the SKT thing was shown by Cavalcanti and the strongly Gaussian by Popovich. And we now have to recall that Kato manifolds sat in a family where they were the central fiber and the nearby fibers were modifications of Hopf. Yeah, so if you assume that this Kato manifold has one of the structures, then the nearby fiber will also have those. But these are now modified Hopf manifolds. And now again, different results tell you that modified Hopf manifolds cannot have neither SKT nor strongly Gaussian metrics. And so again, for strongly Gaussian, this was shown by Popovich, and for SKT, you have this sort of Miyaoka result, which tells you that if you have SKT metric on a complex manifold minus a point, then you also have it on the manifold. But then you show that on a Hopf manifold, you cannot have such a metric. Yeah, so this is just this. But now on the positive side, and this is really where we started looking at this.
Sorry, can you go back to the previous slide? I'm sorry. How do you use the H12 equals 0? I would imagine H21 is usually the thing. It gives you some structure for SKT. How do you?
I don't really know. We really use this as a black box. So this is used at the condition when we say SKT is open under the formation.
Oh, that's how you use it?
That is the moment where we use it. But we do use it as a black box because the proof in itself goes through a generalized a Kähler structure, and this we don't know, and we don't really know how it works. We don't know.
Okay, thank you.
Yeah, I mean, yeah, I cannot say more, but I mean, H12 definitely comes from the fact that you have what? So you have your metric omega, and you look at del bar of omega. You know that del bar of omega is d bar closed. So knowing that this is 0 tells you that this is also d bar exact.
Right.
Right.
Okay.
But then I don't know exactly what to do with this. But this is where this group comes up. And then I really don't know how we use it, but I just know that this is, I mean, this is the hypothesis needed just for the formation part.
Okay, thank you.
Okay. So as I said, there is another, so maybe just as, or not. The notions that I defined before were rather generalizing the Kähler condition by asking that different powers of the fundamental form are closed with respect to different operators. But you can also generalize this in the Kähler condition in another way, which is from a conformal point of view. So now this means that you're not gonna ask, you're gonna ask that your metric is on any neighborhood of the manifold. So on any point has a neighborhood so that your metric is conformal to a local Kähler metric of this manifold. And this can be expressed globally as the condition that the fundamental form satisfies this integral condition. You say d omega is theta with omega, where this theta is a closed real one form called the Lie form of the metric. So if the complex dimension is at least 2, really this Lie form is uniquely determined by this relation. And the remark here is that so this argument that you look, I mean, if you have this closed form, then it is locally exact. So this is what gives you local Kähler metrics, which are conformal to your metric, globalizes to the universal cover. So the universal cover, your closed one form becomes exact. And then you have a global Kähler metric, which is conformal to the pullback of your LCK metric. And moreover, because the fundamental group preserves the Lie form, it will act by translations on this primitive phi of your Lie form, and therefore by strict homotopes on this Kähler metric. So you can also start from actually this description. Let's just start from a Kähler metric on a universal cover on which the P1 acts by homotopes in order to construct not one LCK metric on the manifold, but a conformal class of LCK metrics on the manifold. So these are all multiple ways in which to think of these LCK metrics, or rather structures, because usually LCK metrics. So first of all, of course, the remark is that if you have one LCK metric, then any conformal change of it will also be LCK. And usually you are not interested just in one metric, but in the full conformal class of it. And then, so the positive answer to related these two things is that most, well, not most, but many Kato manifolds admit LCK metric. And the precise condition to know when this happens is when this modification of the ball appearing in the Kato construction, when the modified ball appearing in the Kato construction is Kähler. This is precisely when the resulting Kato manifold will be Kähler. And this we can also show that this is equivalent to asking that the universal cover of the manifold is Kähler. So of course, in particular, if you know that, as I said, this modification, for instance, is a composition of blow-ups along smooth submanifolds, then the resulting modified ball will always be Kähler. Therefore, your manifold will always be LCK. But there are also examples constructed by Hironaka, starting from complex dimension 3, when you can have modifications which are not Kähler. And so then this also gives examples which are not necessarily LCK. And a sketchy proof of this, well, of course, if X is LCK, then as I said, you just pull back and find the primitive and you show that the universal cover is then Kähler. If the universal cover is Kähler, then the modified ball is Kähler. This you essentially show by constructing an embedding of your modified ball minus sigma of 0 inside the universal cover. So, I mean, you can do this attentively, but the point is to sort of understand geometrically what happens with your universal cover. So, your universal cover, as it was, as z copies of this modified ball minus sigma of b, you can think of it as you are just modifying some domain of or just a ball with pi an infinite number of times. So if you just take, well, one domain, you modified it once and then you took out sigma of b. If you glue two copies, then what you did is you composed this modification 2 times and then took out again sigma of b, but of a smaller ball. And then if you do this r times, you have done again this r times and you took out a smaller ball. And using this description, you inductively can construct then this embedding of your modified ball inside of this universal cover. And then by the Miyaoka extension, this gives you first that, well, you know first that the modified ball minus sigma of 0 is Kähler, and then that the modified ball is Kähler. And finally, that the modified ball is Kähler implies that you have a Kähler metric on an LCK metric on the manifold. This is essentially the Brunella construction. And it uses the fact that since we are dealing either with balls or with modified balls, you have potentials. So you can work with those and glue them and modify them in a way that suits you. So first of all, you start with a Kähler metric on the modified ball, and then you start to modify the scalar metric near sigma of B, sigma being this embedding. So when you pull back by sigma this scalar metric, you are on a ball, so this has a potential, so you write it. Then you can pick different constants so that your potential will be bigger than just the standard module of Z, so the standard Puris harmonic function on the ball, let's say, times a constant plus again something. Well, this will be true on some boundary of a ball and smaller on some smaller ball contained in this boundary. So using this, you're going to take a maximum between these two and construct a new metric, which is still the same outside some sigma of smaller ball, but which becomes now the standard flat metric times a constant around sigma of 0, so on a small ball there. And then you redo the same thing, but now you try to modify your new metric near the boundary of the modified ball, but by the same sort of argument. You know that near the boundary of the modified ball, you again have a potential, and you again compare it to the standard module of Z squared potential. It's every time when you compare it to this one, you're going to have to change your constants. You will not be able to just compare it directly with that, but you're going to have to multiply this with some constant, well chosen by the construction. So you will again be able to modify your metric on the outer boundary, but by a different constant times the flat metric. And then because of this, you will have obtained finally some Kähler metric on the modified ball, which is, well, the standard metric times a constant near one boundary and the standard metric times a different constant near the other boundary. So this means that this will give you a Kähler metric on the universal cover, but on which the deck group will act by some strict homotopy, of course, so not by one because it cannot, because otherwise you would have a Kähler metric on the Kato manifold, but by some multiplication of a constant. So this means that this Kähler metric on which P1 acts by homotopes will define to you a conformal class of LCK metrics on the Kato manifold. And in this construction, it's hard to really keep track of what happens to these constants. What you can keep track of is that, in some direction, so the C minus over C plus can be as small as you want, but you don't really know how big it can be. You cannot be one, but you can. So far, we don't really know exactly what are the possible constants you can get, or what is even a bound for these constants. And this is essentially related to, as I said, P1 is isomorphic to Z, so H1 Doram is isomorphic to R in a canonical way. And then the question is, what Lie classes can you realize by LCK metrics? Can you realize like a half line of those, or just some of them, or an open interval? Is it connected or not? Is there a bound? And so this is sort of a geometry inside R of this Lie classes that you can realize in this way, which is the same essentially as knowing what constants you can pick here. So this would give possibly some new invariant of the complex geometry of the Kato manifold, but coming from Hermitian geometry. So just a bit more on LCK manifolds, which should also some kind of motivate to the study of new examples, in particular of Kato manifolds. So there is a special class of LCK manifolds, metrics, which is a class of metrics which is no longer conformally invariant, which are called the Weissman metrics. So you usually say that this is the case when the Lie form is parallel for the Levi-Civita connection. And I will not go too much into this, but the point of this geometry, so of this Weissman matrix, is that we have actually a recipe of constructing many manifolds, so which have Weissman matrix, just starting from polarized scalar manifolds. So on one hand, we have many examples, and on the other hand, we have an important tool which comes from the fact that they have transversally Kähler foliation. So you can use that and do much of the usual Kähler geometry in a transversal way in order to deduce things about your Weissman manifold. So there is one class for which we know a lot. And then you can also obtain some new examples by deforming this. So usually when you deform a Weissman manifold, you are not necessarily Weissman, but you are LCK. And sometimes if you deform, you can still use some arguments which remain open under deformation. But another remark is that, well, these Weissman manifolds have also, Weissman matrix have the property that the corresponding Kähler metric on the universal cover has a global potential. You can actually write it explicitly. I wrote it here. It's not very important what it is, but it has a global potential. So this in particular also tells you that some LCK manifolds will not be able to have this matrix. And this is particularly for all the Kato manifolds which are not Hopf. For Kato manifolds which are not Hopf, you perform the modification. So you had an exceptional divisor. And this exceptional divisor, well, it has multiple components which are compact hypersurfaces. And in the universal cover, they will still remain compact hypersurfaces. It's just that you will have infinitely many components. So in other words, you will have compact, complex submanifolds in your universal cover. And this will not allow you to have then a Kähler metric which has a global potential. And so not only you know that these manifolds don't have Weissman matrix, even they don't have matrix with potential, so they cannot be deformation of Weissman or whatever. So this tells us that we really obtain a new class of LCK manifolds, but also tells us that we cannot no longer use these tools of Weissman geometry or of deformed Weissman manifolds. So we also need to develop some new tools to study them. And this is a general problem in LCK geometry. As soon as you go out of this nice class, you don't really know what to do. Usually things are done case by case. So for instance, one question in LCK geometry that you can try to ask and which is open is their cohomological comparison to Kähler manifolds. As I know, on Kähler manifolds, because you have the Didi-bar lemma, you have the Hodge decomposition, but also the Hodge symmetry. On LCK manifolds, which are not globally conformally Kähler, we know since Weissman already that they don't have the Didi-bar lemma, so you should not hope for this Hodge symmetry. But we still know that, I mean, we know from all the examples that we know that the Crowley has spectral sequence degenerate at first page. So this is true again for all the Weissman manifolds, for things that degenerate, things which are the formation of Weissman. And also is true by case on the examples that we know. So it's true on complex surfaces just because they're complex surfaces. And also on Early-Clauss-Thoma manifolds, which is another class of LCK manifolds. And so, of course, in some sense, it is tempting to just conjecture this is always true, but it is also dangerous to conjecture this because we don't have so many examples outside of this deformation of Weissman manifolds. And so this also tells you again that you also need more examples, but you also need ways of showing this. Okay. And so then we sort of have this in mind, and then we looked at a special class of Kato manifolds which arises using toric geometry, algebraic toric geometry. So we forget now about the matrix, and we just try to redescribe some of the Kato manifolds, but via the algebraic toric tools. So let us first say at which kind of Kato manifolds we look at. So we look at those for which we know that there exists a toric Kato data. So toric Kato data will be in the sense that you can try to guess which would be natural. So you're going to ask that the modification is toric. So this would mean, well, I mean, this modification, you can always extend it to a map from modification of Cn. You just extend it by identity outside of the ball. And you will ask that this modification is a toric modification. So this means that the modified thing is a toric variety and pi is equivalent with respect to the complex torus action. And then to sigma, so to the embedding, you will ask that it is also equivalent, but in a bit weaker sense. So not just equivalent directly with respect to the torus action, but you will ask that there is an automorphism of the torus, so that when you plug in an element of the torus inside of sigma, what comes out is nu of this element times sigma. You need to ask this because if you just ask pure invariance, or so if your nu you want it to be identity, then you will not get much. So this sigma will just have to be one of the toric charts. Yeah, so actually have to allow a bit for a bit weaker condition. Yeah. Yeah. And so starting from this notion, so you're essentially just asking that both these data are compatible with the torus action. We can show that all this sort of kata manifolds, so toric kata manifolds, can be realized via toric geometry. So this means what we exactly do is we can construct an algebraic toric variety, but with non-finite type, meaning it's not covered by finitely many affine chars. So we can construct this algebraic toric variety. Inside of it, we identify one specific open set. Also a group isomorphic to Z, which acts on this toric variety in a way, which is compatible with the torus action, but not invariant to the torus action. So that our kata manifold is precisely the quotient of this open subset in the toric variety by this set action. So
what do you mean by non-finite type? Can you say that?
So if I don't put finite type, usually when you say toric variety, you will think covered by finitely many affine charts. So if non-finite type means I don't ask covered by finitely many charts. So in particular, this span will not be finite. It will have infinitely many cones.
Okay.
Everything else is the same, but there will be infinitely many cones corresponding to infinitely many affine charts. I mean, not necessarily infinitely, but can be infinitely. This is the non-finite type part. And as I said, Oda already realized the Inoue surfaces constructed by Inoue by toric methods. So basically, what we do is to generalize his construction to any dimension. And also some of these manifolds appeared but in a different way in a paper of Tsukihashi, but he didn't really care about Kato manifolds. He was constructing in general some manifolds, and some of those were Kato, but in a bit different way, let's say. But also again from some infinite type, I mean, from this sort of algebraic varieties which are not finite. And how do you construct this? So I'm just gonna try to describe to you how you construct this toric variety. How do you pick the open subset, and how do you pick this group? Yeah, starting from the given toric Kato data. So you have your toric Kato data. Yeah, so you think of it essentially as pi is a toric modification of Cn, and sigma is an embedding. Since the modification of Cn is a toric variety, it is described by a fan. So I did not actually really prepare the slide about toric varieties, but just to say very shortly, toric algebraic varieties can be encoded by so-called fan, which is just a collection of rational cones in Rn. And each cone will correspond, so each n-dimensional cone will correspond to just an affine chart. And when you look at two different cones, and on the face which intersects, which is an intersection of both, will essentially tell you what is the change of coordinates from one chart to the other. So somehow the different vectors appearing in this fan, rational vectors, will tell you what the change of coordinates are each time. And then you can translate all of different kind of geometrical information of your toric variety into different combinatorials of this one. So in any case, from a fan you can construct a toric variety, and conversely, from any toric variety you can associate to it a fan. So in particular, this CN has its associated fan. You will see in a bit some examples of fans, not too many. So we start from this fan. Then we can show that because of this equivalence property that sigma satisfies, actually it has to have a very specific form. It cannot be anything. And namely, it will have to be the composition of one element, which I denoted by lambda underlined, which sits in the complex torus, times one of these affine charts of your toric variety Cn hat. Yeah, and this affine chart will correspond, as I said, to one n-dimensional cone in your fan. So this n-dimensional cone will be generated by n vectors v1, vn, which have all integral components. So if you put them all together in a matrix, you get a J and Z matrix. And then this VA of Z will have this form, at least when you take Z in C star n, let's say, where you can really write coordinates globally. And phi of Z will really have this form, so all the components will be monomers in Z with the powers given by this matrix. So you can show that the equivalence property implies that sigma has this form. So in particular, sigma already determines to you one special cone in this fan, which is identified with one matrix in J and Z. And one element in the complex torus. Now so remembering that you have the fan of your modified Cn and this cone, you can construct a new cone which will be infinite. And this is where your resulting toric variety will have infinitely many affine charts. So what do? You take your fan, which was of the modified Cn, you forget just this cone, so the cone corresponding to sigma. You remember all the other cones, and you take Z copies of those by your matrix A. And so you can think essentially as nu hat minus tau as a fundamental domain for this infinite fan sigma tilde, on which Z acts by multiplication by A. And so you have then many copies of each of your fans. And now, since this matrix A acts on this infinite fan, this will define then naturally an automorphism of the corresponding toric variety associated to the fan. You can even, again, if you pick your coordinates as the coordinates on the complex torus, then this automorphism will really be exactly as phi A, which is written upstairs. And so it will send T1, Tn to these monomers to the powers A1, An. This is exactly the automorphism that you get. And if you want, well, we want this description to be, of course, compatible with our data. So this is not the automorphism you're going to consider. You also have to multiply it with this lambda, which appeared in the sigma in the embedding. And so you also multiply this with lambda, which is an element of the torus. So it also acts on the toric variety. You get gamma, an automorphism of this variety. So you take the group isomorphic to Z generated by this automorphism gamma. No, this is a group which does indeed act on the full variety, but usually doesn't act freely or properly on the full variety. So, I mean, even if you didn't care about your Kato manifold and just wanted to just produce some example of a complex manifold by taking quotient, you cannot at this point just take quotient. You have to pick an open subset inside of it. And this open subset will be exactly the open subset where this group will act freely and properly, especially properly. And this is exactly the so-called stable set of your automorphism. So you're going to take all the all the elements in the complex torus, which go to 0 when you apply gamma many times. So this is just an open subset of the complex torus. And then you're going to take its closure inside of your toric variety. So this open subset is still invariant by gamma by definition. So its closure will also be invariant by gamma. So of course, gamma will act on it. By definition, again, what I wrote here is just its closure. I mean, its closure, you take its closure, but again, it's interior in the toric variety. So what you get is an open subset of this toric variety. So in other words, you have this open subset in the torus, but then you partially compactify it with whatever you want comes from the toric variety. So in the end, you get, I mean, you have this extilled, which is this open subset of the toric variety. You have this group, it acts on it. And this is exactly the universal cover of your Kato manifold. Yeah, so this is, I mean, in order to show this, you actually go into some toric technicalities, but this essentially comes from just understanding, a bit similar to before, but just from trying to understand what is your universal cover. First, trying to understand what is your fundamental domain, and then what happens when you glue these fundamental domains together, you actually get this infinite toric, right? It maybe not over all of it, but some open subset inside of it, and you can it arises in this way. So just a few comments and examples in so remarks also in complex dimension 2. So in general, in complex dimension 2, any modification is composition of blowups. But then if you want it to be a toric, you have to blow up C star fixed 2, so torus invariant points. Points which are fixed. So first you only are allowed to blow up 0 because that's the only fixed point, but then you get the CP1 and then you have 2 points that you can blow up. And then you can again just have always some choices of points to blow up, but not too many. And the remark in dimension 2 is that just knowing this matrix, which describes to you this affine chart given by sigma, just knowing the matrix completely tells you what the blowup is, or in other words, completely determines the blown up C2 that you get globally if you ask the condition that this is minimal. Why? Because this matrix, first of all, since it describes a cone in the modified C2, it has to be a matrix which has only positive components or components which come from the standard vectors you want to. So you can always just put this cone inside of I mean, you have already the fan generated by U1E2, which describes just the fan of C2. Instead of it, you add the cone generated by AE1, AE2, which is the cone where sigma lands into. So this forms the basis, and then what you get here as a fan will be the fan of some algebraic variety which might have singularities. So you usually know if you have or not singularities by knowing if every two-dimensional cone is generated or not by a basis. So then you look at this cone, E1, AE2, it doesn't have any reason to be a basis. So if it's not, you can add new rays and split it more and more until all the cones that you get are indeed generated by basis vector of set 2. And so by taking subdivision of these cones that you get, you have a unique way in which to refine this fan in order to obtain something that is smooth and which is also a modification of C2 in the end. And another remark is that in complex dimension 2, toric Kato surfaces are exactly diagonal Hopf surfaces, or the surfaces constructed with by Inoue with B2 positive. So for diagonal Hopf, what is the picture? The picture is very simple here. As I said, the modification is just the identity. Sigma is just given by some element of the complex torus, but of course, I mean, all of this lambda I have to be modules smaller than 1 because you want that the ball is stand inside the ball. Well, in particular, you have no choice. A has to be just the identity, in particular also because you have no cone here, other than the standard one. So the fan of this is just the fan generated by these standard vectors. How did you get the fan of the infinite cover? We had to forget the cone which corresponded to A. Yeah, so we forget this one. But if you forget the cone corresponding to A and you just remember the rays, what this represents is simply C2 minus 1 point. And so in fact, this two-dimensional cone corresponds to the 0 in the fine chart of this cone. So just erasing this cone is the same geometrically as just erasing 0 from your toric variety. So extended corresponding to this fan will be just C2 minus 0. And then you can see that here this table set corresponding to gamma will just be all of this C2 minus 0. It's not actually smaller, it's really everything. So that again, I mean, you retrieve what you already know about Hopf surfaces or manifolds, which is that you realize them as the quotient of the C2 minus 0, which is a toric variety, which so happens here is of finite type, modulo this gamma, which is just multiplication by some element of the complex torus. So this is something that we already know. Of course, you don't need this. Another example where this fan can become already more complicated is when you only have one blow up at 0. So if you have only one blow up at 0, your fan will be the initial fan, the standard fan, and the blow up will add one ray, which will be the sum of the standard 2 rays coming from the standard vectors. So in particular, we have now two-dimensional cones, which correspond to the two affine charts covering the blow up of C2 at 0. So in this example, which is one of the Inoue surfaces, we pick A to correspond to this cone, so like generated by 1, 0, 1, 1. And sigma, for sigma, you have to take also some lambda. You are not allowed to just take sigma equal to phi A because this would not send the ball inside the ball. You have to also add, to multiply this by 1 and lambda for lambda smaller than 1. And then if you do this construction that I described, well, again, I already said who the fan of the blown up is. But how do you get this infinite fan? You have to remove this cone tau phi. I mean, it's written sigma here. Tau phi, you have to remove it. And then instead of it, just replace it with z copies of what you have. But not directly with that, but with the image of A of that. Yeah, so you have one cone, you have to remove it. So to add A of this cone, A square of this cone, and so on. What does A of this cone do? Well, A of 1, 0 is just 1, 0. So 1, 0 will not get any copies. But A of 0, 1 is 1, 1. And then you will just add Z copies of this. No. So you just get a fan which has 1, 0 once, and then Z copies of the same ray. And A acts on this fan by sending each of these rays to the next one and by fixing 1, 0. So geometrically, each of these rays will correspond to CP1s, each of these rays which are acted on by A. So you will get an infinite string of CP1s in your universal cover, where the 1, 0, because it is isolated, doesn't sit in a two-dimensional cone. will correspond to C star, and A will fix it, but will act on it by multiplication by this lambda. So in your quotient, you will get one rational curve, because A will identify all of these curves between them, and one elliptic curve, which will be C star mod lambda. So by this constructoric description, you can get a rather good understanding of what sort, at least if you only look at torus invariant objects, you get a rather good description, at least in low dimensions, of what sort of things you have, and also how they intersect or don't intersect. And again, this so happens here that in this example, the universal cover of this scatter surface will really be the full toric variety associated to this infinite fan, and not some open subset there. Okay, and then gamma, as I said, you just construct it, as I said, you use lambda and A, and you get this formula for it. Yeah, so you always have very explicit formulas for your all of these things that you construct in every example.
Can I just ask you, you say you like remove this sigma A or tau A.
Yeah.
And then in a sense that gets replaced by this infinite chain of rays.
Yeah.
But I guess maybe I'm confused. Like in the end, is the fan really sort of like the whole upper half space with these rays chosen? Or you're saying it's just like this one skeleton? Is that?
No. So the so what it will cover, I try to draw it. So it's not the full upper half, because minus 1, 0 will never be touched.
Oh,
so there is half a segment completely missing.
Yeah.
And also 1, 0 is really one cone which is isolated from the rest. It doesn't touch the other cones. So it's rather the open half plane to which you add 0 and this one 0. This is the support of the fan.
Yeah.
This is what you're asking. So what I draw, you have to also color the two-dimensional cones where the red appears.
Yeah. Oh, okay.
It's not so correctly drawn. Yeah, so I don't only put the one-dimensional cones, I also put the two-dimensional cones, of course. But only these ones here, and not the ones where there are dots, because... no.
I see. Yeah, okay.
Yeah. Okay. So then another remark is that, okay, in dimension 2, as I said, if you want minimal things, it's basically enough to know this lambda that you chose in your torus and this matrix, and this will just give you. So this is rather combinatorial information, and this will just give you the full surface, but this no longer is true in dimension 3 or bigger. So just knowing the matrix, you don't know everything. And even you can easily start from one matrix and construct different fans having the same middle cone. And you can even construct your modification so that it does not even factorize over the blow up at 0. And so even if you think you're modifying 0, so it must be blow up of 0 then followed by something else, it's not necessarily. And so even in dimension 3, things can, like, you can do basically many things in this construction. So here, I drew two fans which are supposed to be in R3. So really what is drawn is section of these fans for the plane 1, 0, 0, 0, 1, 0, 0, 0, 1. So what appears as a 2 cone is actually a 3 cone, because you have to think of it as the cone from 0. Okay, so these are just 2 examples of of 2 different realizations with the same germ. How you see that this is or not factorizing or the blow up at 0. The blow up at 0, it would be described as the fan where you only have 1, 0, 0, 0, 0, 1, 0, 1, 0, and 1, 1, 1. And the cones corresponding to all of this. So you were going to connect all of these vertices together. So to know whether or not this factorizes over the blowout of 0 would mean that you have a map of fans from this fan to the fan of the blowup over 0 given by the identity. And now you see that because of this cone, red cone here, it actually cuts 1, 0, 0, 1, 1, 1. So 1, 0, 0, 1, 1, 1 in this fan that we drew here is no longer actually a ray in your fan. Yeah, so this means that this is not going to be, this map is not just the identity map on the lattices, it's not going to be a map of toric varieties. So in other words, there is no factorization over this. So this is not blown up over 0. Another remark is that, so on the one hand, because this A describes cones inside of your standard cone defined by 1, 0, 0, 0, 1, and 0, 0, 1, so, well, the third one, all of its components will always be positive or standard vectors, but also conversely is true. You can start from any matrix which has positive components or the standard vectors on the columns and realize it by barycentric subdivision as one cone inside the smooth modification of Cn. Yeah, so in fact, you have a lot of, I mean, both direction works. And this also shows that you have multiple ways of doing so. So some things about the geometry of this. Okay, so as I said, you can actually read many of the properties from the toric picture, some from the fan. But just to say a few words, so you already saw that sometimes this universal cover is actually the full toric variety and sometimes it's not. So in fact, this happens precisely so that the universal cover is the full toric variety. It happens precisely in 2 cases. So first, so in these 2 cases, I have to say, to introduce some combinatorial thing. So you have this matrix, which although does not determine your Kato manifold, determines a lot of the properties of your Kato manifold, in particular some algebraic properties or just the number of holomorphic vector fields and so on. It can determine rather a lot. In particular, it determines something is in A, you might have just columns which are standard columns and which will just correspond to a permutation. So we denote by PA the maximal permutation submatrix of this matrix. This permutation matrix could be just A. So in particular, if A is the identity, that's it. That corresponds to Hopf manifolds. And then you know that the universal cover is just the full toric variety associated to it. It can have rank 1 smaller, so it doesn't have to be of rank n, but n minus 1. In this case, so these are no longer Hopf manifolds, these are indeed new Hopf Kato varieties. But in this case, again, you can show that the universal cover is the full toric variety associated with infinite fan. And I didn't write here, but in all the other cases, the universal cover will be a strict, proper open subset of this toric variety. And then in particular, you can say a bit more when you know that there is absolutely no permutation submatrix in this A. And in this case, you will know, for instance, that this maximal toric divisor of the toric variety will be fully contained in your universal cover, for instance. And sometimes we can even describe this universal cover almost completely, in the sense that, well, not all of it, because of course all of it, you know, it's a toric variety, so you just describe it by the fan. But if you just try to understand which open subset did you pick to close it up in your toric variety, you know what this is when you know, for instance, that A does not have 1 as an eigenvector, eigenvalue. In this case, you can show that this stable set that you took in order to close it up, well, it's not the full C star n, but it's an open subset which is of this form, H times Cn minus 1 modulo Zn. And this also gives the relation of the initial to the initial construction given by Inoue of his surfaces, where he actually started from H times C and then tried to compactify that in some way, or that modulo something, and then try to compactify that. So you can also sort of here go back and try to remove the toric divisors and then see what's your open subset, and you see that in some cases it is actually exactly this sort of open subset. And then you can also understand what can appear geometrically as components of this toric divisor. So in the toric divisor, we have two possibilities. In dimension 2, we saw only rational curves or elliptic curves. In general, you will get either just algebraic toric varieties, yeah, so like CP1, but something more complicated, or instead of elliptic curves, you're going to get some other toric Kato varieties. Yeah, so you're going to have both. You can have both things which are of Keller type, so toric algebraic varieties as you know them, or Kato things, so non-Keller type. Again, this can be made more explicit, so you can actually read from your fan exactly which corresponds to which, but just as an idea. Yeah, and there's all of these divisors. So in fact, in dimension 2, what you get in the end, as I said, you can get one cycle or two, and you usually know when you get one or two, but when you are in dimension 3 or more, you always just get one connected thing. So all of these divisors is gonna meet somewhere. I mean, you can no longer say cycle because you don't know what this means, but they will all intersect. So the full divisor is connected. Okay, and then again, this matrix, so this permutation matrix appearing in our metric will also tell you what sort of invariant curves you can get on your Kato manifold. So when I wrote here T invariant, I mean coming from the torus invariant things on the inversor cover. So you can actually describe exactly and say your manifold is Hopf exactly when all of these invariant curves are elliptic. Your manifold is, we say, hyperbolic type, which is the generic case, meaning that the permutation matrix is small, well, not so big. So this happens exactly when all the invariant curves are rational. And then parabolic is the intermediate case when you have one elliptic curve and then at least one rational curve. But then you can also show that if you have one elliptic curve and one irrational, then the elliptic one is unique and the rational, all the other ones are rational. Yeah, so this parabolic thing, or I mean, this permutation matrix also allows you to see what sort of curves you get and when.
Is this like, this is the same as like parabolic Inoue surface, hyperbolic Inoue surface?
Yeah, of course, this is why we chose this name. Yeah, this is why we chose this name, because in dimension 2 is exactly parabolic and hyperbolic. And when I showed you the example before, you had parabolic, there was one elliptic curve. But
And
parabolic there, yeah.
I guess you don't get like the general, like you're not getting every parabolic Inoue surface and every hyperbolic, are you?
We are getting all of them.
Oh, I see. So every
yes, in dimension 2 we get all of the Inoue things, surfaces, all the hyperbolic and all the parabolic. Yeah.
So it's only missing like these Inoki surfaces.
No, exactly. Inoki, we don't get all the Inokis because I mean, this just tells you that the Inokis are not necessarily toric or something.
I see.
Yeah. So this construction, yeah.
Like these Inoki ones are the only ones you miss, I guess. Is right?
I mean, the only ones we miss from the ones which have very explicit description, because you can always have, I think these were called intermediate type Kato surfaces.
Oh, yeah. Right.
So you have more. It's just that from the traditional old ones, we indeed only miss the Inoki ones. So from the ones which have name, we miss the Inoki ones.
I see.
But then you can always make more, and we don't get those anyways.
Okay.
So actually, I mean, in other words, it's really like a toric Kato surface is exactly an Inoue surface of parabolic or hyperbolic type,
I see.
or a diagonal Hopf surface. So it's
Yeah.
exactly that.
And I guess you sort of explained earlier, sorry, I don't mean to derail, but like you explained earlier that I guess you can characterize exactly how you have to pick the blow-up points for it to be.
Yeah.
Can you say again? Or maybe, I don't know, we can wait.
You have to blow up only fixed points for the torus action. So at first step, you have to blow up 0 because there is no choice. Then you have a CP1. You have 2 choices now. On the CP1, there are 2 points which are fixed. You can pick one of them.
Okay. I
Then
see.
you have a new CP1, and again you have now 3 choices. You have the 2 from before plus 1 new, or 1 from before plus 2 new. So at every point you create yourself more choices, but you always have just a very, a discrete finite number. But always fixed points. Yeah.
Okay. Yeah.
No. Okay. And then, it's rather late, so I will just try to say quickly, anyway, I didn't really prepare details about this, but also how to try to compute invariance of this. So we did not. Okay, so first of all, we showed, this is rather easy, to show that again, the Kodera dimension of this toric Kato manifold is negative. So no canonical, so there are no sections in any power of the canonical bundle. And this comes from the fact that the canonical bundle is essentially anti-effective. Also, we constructed the examples this way, where you have n-2 meromorphic functions. So this was also sort of for LCK manifolds. This was interesting to know, especially since these are not Weissman. And then these are the Hodge numbers that we get. So we could not compute actually all of them. So we couldn't check this question that I asked at some point about the cohomology of LCK manifolds. We could only check it up to k equal to 2. But in particular, we could check that, for instance, this condition that appeared in the Cavalcanti thing, which says that there are no SKT metrics. This was H12, so this one is 0 here. And so the one that we needed for that was there. So why we only have this is because we have different, we use different tools to compute each one of them, and probably some of them you can generalize, but we didn't do because we already found it hard enough to do it. So then we just stopped at that point. So in this result, we have the following thing. So we say, first of all, that toric Kato manifold has no holomorphic forms. For hyperbolic type, so which are most of them, you can compute this invariant, so H0P, H1P, and H11. For parabolic type, we couldn't compute for all of them, actually, but only one lambda is small enough, because we do this by some deformation argument, and then we cannot control for which lambda you can do. And different lambda will give you non-isomorphic parabolic things, because we do have elliptic curves depending on this lambda. So you know that they are not isomorphic, so you cannot just show for one and then deduce for all of them. And moving lambda will give you different deformation of your thing, and you don't know if these numbers remain the same or not. And just a few words about the sort of ideas to compute this. One of them is, of course, since we have toric varieties, is to try to use this. So meaning you're going to compute the cohomology of the sheaves that you're interested in as gamma equivalent cohomology of the same sheaf on the universal cover. Of course, using the fact that your universal cover is toric, and also this sheaf is equivalent for the torus action. And this gamma is Z, so Z cohomology should be easy. And then using, so why is gamma equivalent cohomology? Because there is a spectral sequence given by group cohomology of gamma with values in this gamma module, which is the cohomology of this universal cover, which computes the cohomology that you want. And of course, again, as I said, since gamma is a simple group, so with Z, this group homology vanishes as soon as S is bigger than 1. So the spectral sequence not only degenerates, but even your cohomology is just a direct sum of H0, H1. H0 meaning just gamma invariant, and H1 essentially also gamma invariant by the duality. So we just would have to understand cohomology of these things and then gamma invariant things. Now this doesn't sometimes works and sometimes doesn't, because X-tilde is of not finite type. So also it is an algebraic variety, but we don't know of any Gaga theorems that we can apply so that we could only use algebraic things in order to compute cohomology. And so although it's algebraic, you should in principle use analytic things, so we don't always know how to compute it. But it works, for instance, to show that there are no holomorphic forms. Of course, I mean, for holomorphic forms, you don't need this spectral sequence at all, but I'm just saying here, so for holomorphic forms, for instance, you're going to think of, to show that there are no holomorphic forms, you would have to show that there are no gamma invariant holomorphic forms on the universal cover. And you're going to think of holomorphic forms on the universal cover as being a subshift of holomorphic forms with poles around C, so 1 at n. Why you do that? Because this shape is trivial, and it's just generated by these forms, and so it's much easier to just see what the global sections of this are, and then you say holomorphic form is one of these which has no poles. And then the point is, okay, so the global shift of this would have to be just this times the global functions of X-tilde. And then we show that when X is hyperbolic, X-tilde has no holomorphic functions except the constants. And when X is parabolic, there are holomorphic functions which are just given in one variable. So holomorphic functions is the same as 4 functions on C. So then you could have actually only 1 holomorphic forms on this universal cover, but then you can write exactly what they look like, look how gamma acts on them, and see that although you can have holomorphic 1 forms, in the parabolic case, there are no gamma invariant ones. And so just using toric description and gamma invariance, you can rather easily detect non-existence of forms. Okay, so for forms it's fine, but then for higher things you need a bit more ideas or something more. You cannot just do this. And another idea was then to use semi-continuity results from this, in some sense, to obtain some inequalities, and then from semi-continuity result to get some inequalities in another sense, and try to combine this in order to get what we expect. And then for this, we generalized construction given by Nakamura in dimension 2, and also another one. So we actually gave 2 different constructions, also given by Tsukihashi in his paper with his construction, which does the following thing. So if you start from any toric atom manifold of hyperbolic type, you can construct a family such that your manifold, so all the smooth fibers are your given hyperbolic, biholomorphic to your given hyperbolic type atom manifold, while the central one is a singular algebraic variety, which it's not just singular, it's a non-normal algebraic variety, which you obtain exactly from an algebraic compact toric variety, in which you have 2 invariant hypersurfaces which you glue together. And so the normalization is just just a toric compact algebraic variety, but you have to glue these 2 things. And we do this construction again with the fan. So we actually just construct the fan starting from the fan describing the universal cover. So we actually do the formation of the universal cover, but also the formation of the gamma group on the universal cover. So to be able to control what's the fiber over every point. So because this works for hyperbolic, so that all the fibers are the same around 0, you can directly use this semi-continuity arguments for those and say directly if you know something about the central fiber, which is singular but also algebraic, so you can use some of the things that you know about that. You can deduce what you want for any hyperbolic. But for parabolic, you can do a different construction, so different families, which is rather similar to this one, except you can no longer make all the nearby fibers isomorphic. So the nearby fibers will actually be non-isomorphic. So then you can apply the same argument only for nearby fibers to 0, but you don't have really control to how far you can go. And then, I mean, just the last slide here is very sketchy, but is what I said, how to compute this other. So this Hodge numbers of type H0Q is, on one hand, you have upper semi-continuity. On the other hand, the singular fiber is singular, but you can still use, for this sheaf, at least for the sheaf of holomorphic functions, you can use the normalization sequence, which will allow you to compute the cohomology of this singular fiber. And because you know what's the double locus, which is just a compact algebraic variety, and you also know what's the normalization, so you can do the rest. And then for H1P, it's really a combination of these two, but it becomes more involved. And then we stopped there because already at that point it was more complicated. Okay, but this was just to. Okay, I also have a slide about Betti numbers, but in terms of toric things. But the point, all of these points is just to say more that at least to some point, the toric tools allowed us to compute things. So this was good. And then the hope is also, and this is, I didn't have a slide about this, but I just said briefly about this question of what are the Lie classes that you can get for the LCK matrix. So this, we didn't look into this, but the hope is also that you, for the toric Kato manifolds, you can again use this toric geometry in order to produce a new construction of LCK matrix, but of matrix which will be also compatible with the toric things. And then possibly also be able to then really control more what is happening. So what are these constants that appear? And we try to describe this set. But this is something we did not do. We just hope that it would be possible to do. Okay, and then we stop here.
Okay, yeah. Thank you.
Thanks.
Thanks.
No.